To amplify a slow-moving acoustic wave, you can use a fast-moving electromagnetic pump wave. When you drive this high-frequency wave into a crystal lattice placed inside a magnetic field, the waves interact, transferring energy and causing the acoustic phonon wave to grow. Our objective is to derive the exact mathematical expression that measures how efficiently the crystal performs this energy transfer. We call this material property the nonlinear optical susceptibility, or chi sub En. To find this macroscopic property, we have to start at the microscopic level. We need to track the electron plasma moving through the material using 5 core hydrodynamic equations. This document outlines the theoretical formulation. We start with the momentum transfer equation, followed by the first-order equation of motion, the electron continuity equation, Poisson's equation for the space charge field, and finally, the equation of motion for the lattice itself. On their own, these fluid dynamics and Maxwell's equations describe isolated behaviors. By mathematically linking them together, we can calculate the true amplification potential of the semiconductor plasma. We begin by combining our base equations. Under the section differentiating with respect to time, we apply a time derivative to the continuity equation for the electrons. With the derivative expanded, we substitute the momentum transfer equations directly into this continuity equation. In the top half, the partial derivative of v1 with respect to x represents momentum damping, and the adjacent term is the convective derivative. Because we have long wavelength perturbations, the convective derivative is extremely small, allowing us to safely eliminate it from the expression. Moving down to equation 6, you'll see the total force on the density perturbation is modified by collisions and the applied magnetic field. We group these specific forces into a single variable, the effective plasma frequency, denoted as omega bar sub p squared. By pruning the negligible terms and grouping the constants, we arrive at a unified master perturbation equation. We now have a mathematical framework to track exactly how the different waves interact within the plasma. Look at the perturbation splitting section. Total density N1 is the sum of a fast-varying part, Nf, and a slow-varying part, Ns. To satisfy phase matching, we apply the rotating wave approximation, splitting our master equation into 2 uncoupled formulas tracking the fast and slow waves. Take a look at the differential equation for the fast wave. How would you convert these derivatives into the Fourier domain? By assuming the fast wave varies exponentially, the time derivatives become -I times omega 1, and spatial derivatives become I times k. The complex calculus reduces to algebraic multipliers, allowing us to cleanly isolate Nf. Translating the problem into the frequency domain allows us to bypass the differential equations entirely. We can solve for the wave interactions using straight algebra. With the wave equations defined, we use our expression for the slow density wave in equation 8 to calculate the induced current density, J1. To keep the calculations manageable, look at the steps for the 0th order velocity. By assuming a weak applied magnetic field, B0 approaches 0, which greatly simplifies the electron velocity components. Applying this weak field condition near resonance, we arrive at equation 13 for the current density. Integrating this J1 with respect to time directly gives us the induced polarization of the crystal, our bridge back to the physical material. The induced polarization is defined by the electric fields acting on the material, making it directly proportional to our target, the nonlinear optical susceptibility. As shown in the top equations, we rearrange the terms to solve for chi sub En. We have successfully mapped the physical interaction of sound and light waves down to a specific optical property. But our resulting expression contains imaginary numbers and complex fractions that need to be cleaned up before they are useful for experimental measurements. The final mathematical hurdle lies in the denominator. Our susceptibility equation is divided by a complex expression, delta, which consists of both a real part, r, and an imaginary part, I. To resolve this, we multiply both the numerator and the denominator by the complex conjugate, r minus I times I. This standard algebraic strategy eliminates the imaginary unit from the denominator, allowing us to separate the expression. From there, we isolate the components. We carefully group the terms to extract just the real component, substituting our physical variables back into r to build out the full fraction. Finally, we arrive at the boxed equation, yielding the rationalized expression for the real part of the nonlinear susceptibility, chi sub En r. This exact metric tells us the amplification efficiency. Let's review the exact path we took. We started with the 5 base hydrodynamic equations. We combined them into a master density perturbation equation. We applied the rotating wave approximation to split the fast and slow waves, moved into the Fourier domain to simplify the math, calculated the current and polarization, and finally rationalized the fraction to extract the susceptibility. This step-by-step mathematical translation from raw fluid dynamics to optical metrics is what allows us to accurately predict how efficiently a semiconductor plasma can amplify acoustic waves in the real world.